Okie dokie, physical science time. Someone should have taken a lunch count first. The video is going to contain us taking lunch count. Lunch today, I do know, was cheeseburger casserole. Put your hands in the air like you just don't care for cheeseburger casserole. Mason, Corbin, anyone else? Anything for B? No B's? He just did it at the wrong time just to be a pest. Okay, well that's fine. Okay, speaking of physical science time, like we were about cheeseburger casserole, that's the segue, is that we were speaking about cheeseburger casserole and now we're speaking about physical science. Today's lesson is about the elements. The elements. The objective reads, if someone could please read it to me, it's hard for me to see it from here. Evaluate and communicate. Hopefully you met both of those verbs in your lab. Although I guess in this case I am going to evaluate and communicate. Information. Ooh, ran out of room. About elements. I'm going to put a little plus sign this time. And their properties. Let me remind you for the let me cause you to remind me for the 40th time. What's a property? What does the word property mean in science? What are we talking about when we talk about properties? There are other properties besides physicals, but yeah, the characteristics, the identifying characteristics of that object, its properties. So let's say some properties just for fun of Corbin. In his appearance. Glasses, right? I'll start you out. What else? Hoodie. Hoodie that shows up in the dark, yes. Drippy shoes, brown hair. Some would say curly hair. Skin color of a Caucasian person. That's just, like, you wouldn't say white because that's not true. I mean, this is one of the things I'm on, is that this is the color white. And this really isn't, right? Like everyone's different shades of pinkish brown. That's how human beings are. Why would you have to include that in your YouTube video about science? Great question. Let's move on to talk about the elements properties. So like Corbin, like everything, the elements have various properties. And I think what we're primarily going to do is this. And I want you to draw this in your book or your notes, which you are taking notes. No, it's a good drawing. I'm good at it. I did do this one a little bit lopsided. I mean, the whole thing's got to be kind of lopsided. I'm doing it by hand and memory. Can you tell what I would draw in here? But wait, there's more. The periodic table of the elements. So you should start by drawing that. And I think we will be able to get through this whole lesson with you knowing the things that you need to know if we just have this diagram and you listen to me. So those are the two requirements. Draw this diagram along with me and listen to me. It might be helpful if you have the man-made as opposed to boy-made periodic table that you own with you so that you can see what I'm talking about if you can't see the board over there. So that might be helpful, but that's not necessarily a requirement. And even if you have this, don't trick yourself into thinking, oh, I'll just put it down on, you won't. Just draw it like I'm drawing it, okay? If I'm spending the time to draw this, even though I have it, and I also have it in my mind where you don't, then you should take the time to draw this too, okay? And that's one of my fundamental philosophies of note-taking, is that if I'm going to the trouble of doing this, even though I already know it, you should go to the trouble of doing it because you don't know it. So let's start out with, what are these? What are we going to indicate as the boxes on here? Elements, which is a certain kind of what? Atom. Yeah, it's a kind of atom that has all of the properties, or an atom is a particle that has all the properties of an element, and therefore an element is a particular set of properties of one kind of atom, determined primarily by what? What's the primary thing? What is actually the definition of what determines what element that is? The number of protons. And that since you remember how we calculated protons, neutrons, and electrons, you remember that affects how many electrons there are, and that's what gives it its chemical properties. Remember we talked about valence electrons are what give it its chemical properties. The different groups have similar chemical properties, which we'll talk about again, because of their valence electrons, which is in a roundabout way determined by their protons, which is what that element is. So individual boxes are going to be elements. Let's draw, let me switch back to blue real quick. Let's draw, now that I've come over here, let's draw this little box. This is going to be like a blown up version. What's your favorite element? Corbin, what's your favorite element, or do you have one? Could you make one up real quick? Let me start over. AG. Okay, we got AG. Okay, so I want you to, you don't have to use AG in yours, but in a blown up box, we're going to indicate the thing. So what is that? What have I just drawn in the box? We aren't going to label the box, but what's in the box that I have put there? Okay, but what is that? This thing here, it looks like letters, but we call it a chemical what? Do you remember? This was one of your vocab words, I think, 2 chapters ago. Might have been a vocab word this chapter. Chemical looks like letters, but we call it a chemical symbol. Have you heard that before? Yeah. Oof. Was that in your vocab, though, for this time?
This time?
Yeah. This is the chemical symbol, and we've chosen this one, and so AG is the chemical symbol. Underneath or above, it doesn't really matter where, we have its name. And what is the name of this if it's AG?
Silver.
Silver. So we'll have its name somewhere on there. What else will be contained in that little box, importantly? Yeah, it's atomic number, which for that one it is what?
47.
Yeah, and the periodic table on the wall shows it in red, so why don't I also show it in red? 47. Does it have to be 47? To be silver, it does. Atomic number. What else information is on there? Thank you. I'm so glad you said it like that. Average atomic mass, which for silver is what? Well, it's someone else then. Or look at your periodic table that you've been issued.
107.
Point, surely, something, right?
0.87.
107.87 is its average atomic mass. Does that mean every atom of silver has an atomic mass of 107.87? No, in fact, no atom of silver can have a mass of 107.87 because it's only whole numbers. So this is an average. Is it possible to have only whole numbers in a set and have them average to a decimal? Of course it is. Yeah, if you have 2 and 1, the average of that, even though those are both whole numbers, is 1.5. Right, that's already a decimal. So only whole numbers for individual atoms, but on average, the average atomic mass, and in fact that's a weighted average, which we'll talk about in chemistry, but the average atomic mass for silver is 107.87. What other information is on there? I mean, this one has quite a lot of stuff. It has its density, it has its electron configuration, it has its boiling point and melting point, it has its oxidation states. We don't need all of that, but what other information do we need from there? Probably. You see, there's something else that's missing. Or maybe this is shown better. It's not really on that, but it is shown better in your book. There's one other thing we're looking for here. Can you turn, I think in your book it's at the very, very back. There's one other kind of important piece of information that your book indicates that we don't really see. Yes, the state of matter at room temperature. And so I think in your book that's indicated by a little symbol. On some periodic tables, it's indicated by a colored outline. On this one, it breaks down not only whether it's a solid, liquid, or gas, but what kind of solid, liquid, and gas. But for us, let's just leave it at that it's solid at room temperature. Your book indicates that by a little gray cube, I think. And so we'll just put a little gray cube on there. State of matter. Okay, so those are all the information that the individual boxes tell us. Now let's talk about the periodic table in general. What does it mean for something to be periodic?
Periods.
Yep, periods. What's that mean? Yeah, it's a pattern. It's a repeating pattern in time is a period. A period is how long it takes for that pattern to repeat. So for instance, the pattern of the moon phases is 29 days-ish. So that means every 29 days the moon repeats. The period of a quarterly magazine is once a quarter, once every 3 months, once every quarter of a year. The period of the Crawford Clippard is once a week, right? So it's periodical. And in fact, the reason I pick magazines and newspapers for that is because we call those documents periodicals. I don't know if you've ever heard anyone call those that, but that means they're continually, maybe not forever, but continually over and over again issued. They're periodic. So this, in the same way, the periodic table has a repeating pattern, a period, and that repeating pattern is shown. We are not going to fill out every element here, but what we are going to do is show where the periods are. So we have, oh, I did this this is too big over here. I want it to be even. I'm going to try to make this really nice. I'm not really good at things, but I'm going to try to make this really nice. Does that look roughly even to you guys? But why did I make it go down so low? This doesn't need to be that tall. Basically, this is Bob Ross podcast. Does that look pretty even?
Yeah.
I think so. Yeah, okay, so this is period what? If you were to invent the periodic table, what would you number this period? 1. That's a great idea. In fact, that's how it is numbered. That's period 1. What about this one? Really good. You guys are on a roll. And someone who's not Aiden Streety. What about this one? He's getting too many of these right. What about this one? Great job. What about this one?
I don't know. Oh.
Oof. Yeah, no, we can't rely on him anymore. What about this one? Don't say it anymore. Someone else needs to have a chance. Thank you. You really showed your mettle there, Joe. Now what about this one? And this one? Whew, okay, good. I almost gave it away by writing it. So those are the periods of the periodic table. And what's true in a period is that we see a repeating pattern. It's not the exact same pattern every time, but a repeating pattern of properties. In fact, that's how, when this was kind of invented by Dmitry Mendeleev is the man's name. Let me see if I can write it in Russian. Oops, backwards. Like a child. Oh no, I've run out of room. And I also forgot L. What's the O look like? Is it that? I think so. I've run out of room. Dmitry Mendeleev, and I guess just to show off, I've also written it in Russian. But when he invented this, the way he invented it, the pattern of the elements, is that the properties of these elements have been understood for about between 50 and 100 years. By Antoine Lavoisier was the first to kind of sort them by their properties. He was French. And then Mendeleev, a Russian, organized them in order of their properties and found this repeating pattern and organized them this way. And it has these gaps, a larger gap here and here, because those properties don't really exist as such in those periods. And so we'll talk about what the different properties are in a second. But basically it's organized by how the patterns repeat. So these ones, hydrogen and helium, are both gases. And they're a little bit different from the rest. This is just a very brief period. But then we get lithium, beryllium, which are both light metals. Lithium is very reactive, explosively reactive. Beryllium is not quite as reactive, but still reactive and light. And then we get boron, which is a fairly non-reactive metal. And then carbon, which is a non-metal. And then nitrogen, and then oxygen, and those start to be gases. And he saw that pattern, and then a noble gas, which actually hadn't been discovered yet, but we now know there are noble gases. And then the pattern repeats itself. An explosive light metal, a less reactive light metal, an almost non-reactive light metal, and then the pattern repeats. In this period, in this period, the universe adds transition metals, which are roughly non-reactive. They do react, but they're not very reactive. And then it repeats. And then in this period, other metals are added. I'm sorry. This down here is also 6, and this down here is also 7. Because in reality, these two periods squish in right here. these two periods, I'll do it for the camera, squish in right here. And so a better way to draw it, although it would take up a lot more horizontal room, oops. I may have made it even a little too big, but as well, hold on. There. With these squished in there. But that takes up a lot too much room, and so we don't usually indicate it that way. But these two rows that are usually shown below actually go in there in periods 6 and 7. And those are called the rare earth metals, which I think is one of your vocab words. But anyway, back to Mendeleev. He organized them by their properties in repeating patterns, and then we call that the periodic table because those patterns repeat. So what is the repeating pattern? Well, in group 1, we've labeled the periods. Let's now label the groups. Let's do it in blue. In group 1, or what is sometimes called 1A in the old naming, we have hydrogen, which is a reactive gas, and then the rest of them are all very reactive metals. Remember, how many valence electrons do these things have? 1. They have 1 valence electron. Let me tell you, this is a little bit jumping the gun because we'll talk more about this in chapter 20, but there's this idea of what's called the octet rule. Can you guess what the root word of octet rule is? Oct, which is what? 8. The octet rule means that each, I guess we'll put atom, I'm going to put in quotes, wants 8 valence electrons. Each atom wants, why would I put that in quotes, do you think? They can't. They probably, we don't really know, but they probably can't think. But they are more stable with 8. Changes occur if they're left alone to cause them to have 8, if they're, as it were, left to their own devices. So each atom wants 8 valence electrons. If these ones have 1 valence electron, that's why they're so reactive. They really want to get rid of that 1 valence electron so that they can have a full valence shell. So these are very reactive metals. Group 1 are called the alkali metals. You should write that down. Very reactive. And in fact, I'm even going to cross out very and put explosively reactive. With what? Do you know? I think Cameron probably knows. What do they explosively react with? You've probably seen this on YouTube Shorts. Yes, but that's not it. Water. You might have seen on, I guess, probably Facebook Reels, because you guys are all boomers, if someone drops a piece of lithium or sodium or potassium in water and it explodes, and if there's time after this lesson, we'll go do that in the lab. But these react explosively. That's group 1, the alkali metals. Group 2 are called the alkaline, little different word, earth metals. And they are less reactive. The alkaline earth metals are less reactive. But they still do, they're still very reactive, but they don't react explosively. They might react even violently, but not usually explosively. And then these here in the middle are groups 3 through 12. And this is called, I already said it, but these are called the transition metals. Sometimes these ones are called, I called them earlier the rare earth metals, that's fine, but they're also sometimes called the inner transition metals. So you should label these on your little diagram.
Label them what?
This whole chunk here is the transition metals, and this whole chunk is the inner transition metals. And that's really all we're going to say about those for now. What do you see a recurring theme here so far between all of these? What's true of all of these so far that we've said? They're metals. And that's because we talked about this during the last test, I think, actually, but there's this, you remember this little guy? What do we call him? Do you remember? Yeah, this is called the stair-step line. This is a very important part of the periodic table. And it separates, basically, on this side of it are the metals, and on this side are the non-metals. And anything touching it, except aluminum, are metalloids. So if it's actually adjacent, if it's touching the stair-step line, that's considered a metalloid, except aluminum. Aluminum is a metal. So boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, maybe livermorium and tennessine are metalloids. And can you guess what property of these atoms makes it so that they are either metals or nonmetals? Basically, it's their number of, specifically, valence electrons. So these ones have a number of valence electrons that they like to get rid of them. Metals like to get rid of electrons when they bond. And these ones, in general, have a number of electrons that they like to gain them. And that causes them to have properties of nonmetals. So speaking thereof, we have now group 4, which I guess I'm doing in, well, I'll do this in a different color. Not blue still, but I'm not going to do it in red either because that was our stair-step line. What color do you think? Brown. That's a great suggestion. Thank you. So we'll have here group 4, sometimes called group 14. Group 4, we usually just call it the boron group. It has a fancy name, the icosagens. And these are, boron's a fairly non-reactive metalloid, aluminum is a fairly non-reactive metal, gallium, indium, and thallium are fairly non-reactive metals. Interestingly, indium is, according to Vsauce Michael, at Vsauce Michael, I'll put a link to his channel in the description. I'm just kidding, I'm not going to do stuff like that. But he says that indium is the only metal on the periodic table, or the only element on the periodic table you can take a bite of, and you'd probably be fine. It's soft enough that you could bite it, non-toxic enough that you'd probably be fine, and it's a solid, like the gases. There are gases that's true of, like oxygen, but you can't bite a gas. That's ridiculous. And so indium is the one. He has a chunk of indium, and he takes a bite of it, and he chews it up like gum and swallows it. And we're like, what? Why would you do that, Vsauce Michael? But it's fine. He's still alive. I've seen him on YouTube since then. So again, at Vsauce Michael. I don't think that's actually the name of the channel. I think it's just Vsauce. Anyway, the next one, group 5. Group 5 we have, oh, I'm sorry, I've mislabeled these. This one was 3. This one was 3. Forgive me. This one was 3. This one is 4. Conveniently, since I'm doing Roman numerals, I can just pretend like I didn't even mess that up. 3 was the icosagens. 4 is usually called the carbon group. And these are sometimes, by fancy people, called the crystallogens. Although I had to look both of these up, and so I don't think people usually use them. These are also, they're not just non-reactive, but they are not really self-reactive, but they will chain. Both carbon and silicon and possibly germanium will chain together. That's one of the ways that there is life, is because carbon so easily bonds with itself, and most of the things that make you up involve carbon-carbon bonds. And so we are said to be, according to Star Trek, carbon-based life forms, meaning that most of the molecules that make us us, even though you're 70% water, the ones that make you you and not a puddle, are carbon bonds. Okay, next we have group 5. Group 5 is sometimes called the nitrogen group, although this one, now we get into the ones that really are most commonly. We do call this usually the pnictogens. Fairly reactive, but non-metals. And so nitrogen, interestingly, does make up most of the atmosphere. Nitrogen as an atom is quite reactive, but it bonds with itself in the strongest bond that we know of in the universe. The nitrogen-nitrogen triple bond is the strongest bond in the universe, and so it's extremely non-reactive when it's self-bonded, when it exists as an N2 atom. And so that's most of the air you breathe. About 78% of the air you breathe is just inert nitrogen. Next we have group 6. Which is the oxygen group, or sometimes usually called the chalcogens, which means generators of chalk. The suffix gens means makers of. These are all quite reactive. Oxygen is very reactive. Oxygen as O2, kind of like nitrogen, it exists usually in nature as just O2 bonded with itself. That's even still a little reactive, but the oxygen atom as just O is very reactive. So these are all reactive nonmetals, but not as reactive as group 7, which you recognize some of these. I'm going to start over up here. These are the halogens. And I'm not even going to put that in quotes. We always call this the halogens. No one calls it the fluorine group. That's just right out. We always call it the halogens. And these all have how many valence electrons? If they're in group 7? 7. They have 7 valence electrons. Remember the octet rule. They're most stable with 8. And so like group 1, that was very reactive because it wants to get rid of 1 electron, these are very reactive because they only need 1 more electron. They'll react violently to get 1 more electron. Extremely reactive. Again, probably explosively reactive. And then finally, we have group 8, which are called the noble gases. These are non-reactive. Using what you know about what I've told you today, why would these be non-reactive? They already have 8. If all the atoms want 8, all, not hydrogen and helium, want 8, and these ones have 8, they're content. That's a lesson you should live in your life, right? If you say you want $100, then when you get $100, don't be like, no, I want 1,000. Because that's the American dream, but that's a lie, I'm telling you. Be happy with what you have if what you have is enough, like the noble gases.